Yes. So in the last class we discussed about the classification of the elements and their brief history, how the elements are classified at 18th century or in 1865, or currently how the classification of the elements are done. In the last class we discussed about the modern periodic table, that is modern periodic law, and now we classified the elements that based upon the periodic functions of their atomic number. Therefore, the physical and chemical properties are the periodic functions of their atomic number. That is why they are classified. That is called as a modern periodic law. Modern periodic law. Modern periodic law. That is, physical and chemical properties are based upon their atomic number. Atomic number. Now, based upon this electronic configuration, what we discussed yesterday, the elements are classified into S block elements, P block, D and F block elements, SPDF block elements. Now, how these elements are classified? S block elements. In the last class we discussed about the S block elements. These are the group of elements where the valence electrons are added to the outer S atomic orbital of an atom. S block elements are the group of elements, that is group number 1 and group number 2, where the valence electrons are added to the outer S atomic orbital of an atom. They are represented by the general electronic configuration, whereas the group number 1, the general electronic configuration is NS1. For group number 2, the general electronic configuration is NS2. Therefore, Ns to the power of 0.2. This is the general electronic configuration of S block elements. General electronic configuration. General electronic configuration of S block elements. General electronic configuration of S block elements. Now, in the S block elements, in group number 1, we have 7 elements. In group number 2, we have 6 elements. Group number 2, we have 6 elements. Therefore, total 13 elements are there in S block elements. Now, out of this 7 elements in the first group, hydrogen is a non-metal because it occurs in gaseous state at lab temperature. And the last element, that is a francium, that possesses unstable nuclei. Because with the increase in mass number, the stability of the nucleus decreases, and hence it is considered as a radioactive element. Excluding these two, we have the elements from lithium to cesium. They are considered as metals. Therefore, these 5 elements are called alkali metals. Number of elements are 7, but the alkali metals are 5. Now, these are called as alkali metals. Why? Because when they dissolve in water, they give hydroxy compound like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. The hydroxides of these compounds are formed. They are soluble in water. Therefore, the hydroxides are considered as a basis actually All bases are not soluble in water, but alkali hydroxides are soluble in water. Therefore, all alkalis are bases, but all bases are not alkalis. All alkalis are bases, but all bases are not alkalis. This implies group number 1 hydroxides, metallic hydroxides are soluble in water. The remaining metal hydroxides, group number 2 metal hydroxides, they may or may not be soluble in water. Usually they are not soluble in water. In group number 2, later we come across the periodic properties of each one of the compounds. There are elements. Now with respect to trend in the atomic size or in atomic radius or in the ionization potential value or electropositivity value or electronegativity value or electron affinity value, we will discuss later one by one. Now what are these two groups are collectively called as a representative elements. These are called as a representative elements. When you come across the group number 13 onwards, group number 13, group number 14, group number 15, group number 16, group number 17 and group number 18. 1, 2, 3, 4, 5, 6. These 6 numbers of the groups, they fall in the right side of the modern periodic table, whereas the group number 13 elements, they have the electronic configuration NS2NP1 configuration. Group number 14 elements, very important class of these elements are called carbon family elements. Carbon family elements. Whereas the outer electronic configuration is NS2NP2 configuration. NS2NP2 configuration. Whereas group number 15 elements, they are NS2NP3 electronic configuration. Group number 16 elements, NS2NP4 configuration. Group number 17 elements, NS2NP5 configuration, and group number 18 elements, NS2NP6 configuration. See, the inner atomic orbital, yes, they have fixed number of the electrons. There is outer p atomic orbital, usually electrons are added in one number, P1, P2, P3, P4, P5, P6 configuration. Whereas the group number 13 elements starting at that of the boron, therefore they are often called as a boron family elements. Whereas the group number 14, usually it begins with carbon, therefore often they are considered as a carbon family elements. Whereas the group number similarly 15, 16, 17 and 18, you know that the 18th group elements, they are considered as a inert gases or noble gases because they have octet structure, whereas the s atomic orbital has capacity for the accommodation of 2 electrons, therefore NS2 is there, which confirms the octet state of the s atomic orbital. Whereas the p atomic orbital, yesterday we discussed, it has the ability to accommodate 6 numbers of the electrons. That confirms the stability of the p atomic orbital. Therefore, S is octet and P is octet. Therefore, no free valence electrons are available for the chemical bond formation. Therefore, they are considered as inert, chemically inert. They won't react under normal conditions. Therefore, they are called as noble gases. They are considered as inert gases. It includes helium, neon, argon, krypton and xenon and radon. These elements present in 18th group of the modern periodic table. Whereas in 17th group, You know that most electronegative elements among the modern periodic table, they are located in the 17th group of the modern periodic table. Starting from the fluorine, chlorine, bromine, iodine, and acetylene, that is a radioactive halogen. These elements are present. They have the general electronic configuration Ns2, Np5. They are considered as a halogen family elements. They are considered as a halogen family elements. Now, this group number 16 elements are there. They begins with that of the oxygen. Therefore, that's a oxygen family elements. Oxygen family elements. Oxygen family elements. They have the electronic configuration. See how to remember these numbers. 2 plus 1 is equal to 3. In unit place we have 3. 2 plus 2 is equal to 4. In unit place we have 4. Whereas 2 plus 3 is 5. In unit place we have 5. Whereas 2 plus 4 is equal to 6. In unit place we have 6. 2 plus 5 is equal to 7. In unit place we have 7. 2 plus 6 is equal to 8. In unit place we have 8. Now usually it begins with that of the nitrogen. Therefore they are considered as a nitrogen family elements. Nitrogen family elements. Therefore here we have boron family elements, carbon family elements, nitrogen family elements, oxygen family elements, halogen family elements, zero group elements are inert gases or noble gases. These are considered as zero group elements. Zero group because the valence is 0 are noble gases. They are often called as noble gases. Okay. Now this that begins with Ns2 is common. There is a pin atomic orbital. We have the valence electrons. Therefore, Ns2 Np to the power of 1 to 6. Now this refers to the general electronic configuration of the p block elements. General electronic configuration of p block elements. General electronic configuration of the p block elements. Electronic configuration of p block elements. Whereas very important, here n is greater than or equal to 2. Because when you put n is equal to 1, 1s2 1p6 is not there. 1s2 1p1 1 like that it is not there. Whereas the helium that possesses 1s2 configuration. Therefore here a very important specification, n is greater than or equal to 2. Because here starting from that the boron has 2s2 2p2 configuration, 2s2 2p2 configuration, 2s2 2p2 configuration. 2p1 configuration. Here we have 2s2. When it comes under third, that is a ns2 np2. By putting n is equal to 2, 2s2 2p2 configuration. By putting n is equal to 2, 2s2 2p3 configuration. That is for nitrogen. By putting n is equal to 2, 2s2 2p4 configuration. That is for oxygen. By putting n is equal to 2, 2s2 2p5 configuration, that is for fluorine, the first member. There is a 2s2 2p6 configuration, that is for neon electronic configuration. Neon electronic configuration. Here also they are very important. Here n is greater than or equal to 1. N is greater than or equal to 1 for group number 1 elements. For group number 1 elements. N is greater than or equal to 2 for group number 2 elements. Where is it? 1s2 is not there for group number 1 electronic configuration. That is the most precise form for a representation of the electronic configuration. Just by putting ns1 configuration, it's not so sufficient by putting n value, that is n is greater than or equal to 1. Here also you can predict the n value, n is greater than or equal to 2. That is starting from that of this beryllium. Beryllium in the general electronic configuration, 2s2 configuration, whereas next we come across 3s2 configuration for magnesium, 4s2 configuration for calcium, and so on. Now, what are the S block elements and P block? Group of elements for which the valence electrons are added to the outer p atomic orbital of an atom are called P block elements. Usually in P block elements, you know that the S block elements, they include some metals, alkali metals and alkaline earth metals. Because these metals, they found on the surface of the earth crust in the form of the calcium carbonate, magnesium carbonate, or dolomite, or barium carbonate. That is why they found on the surface of the earth crust, and hence they are considered as alkaline earth metals. Whereas in group number 13, 14 up to 18, the valence electrons are added to the outer s atomic orbital, outer p atomic orbital of an atom. Therefore, group of elements for which the valence electrons are present are added to the outer p atomic orbital of an atom are called P block elements. They include metals, non-metals, and metalloids. Most of the elements in P block are considered as non-metals, but some of the elements, they exhibit metallic character. For example, aluminum belongs to P block, but it exhibits metallic character. Where the silicon and germanium, they belongs to the P block. They at low temperature, they exhibit non-metallic character, but high temperature, they exhibit metallic character. They exhibit both the properties. Therefore, they are, in such cases, they are considered as metalloids. Metallic property as well as non-metallic properties are predicted in such type of the elements. Is it clear? Where is the non-metals? You are very familiar with that of the non-metals. Usually non-metals are either gaseous at lab temperature or liquids with low boiling point at lab temperature or solid with low melting point at lab temperature. For example, just to see the physical state of the fluorine, chlorine gases at lab temperature. Bromine, liquid at lab temperature. Iodine, solid at lab temperature, but it exhibits very important property like that of the camphor. What is that property? Sublimation property. On heating, it does not give the liquid or fluid state, directly it changes to the vapor phase. Therefore, the beautiful violet vapors are formed when iodine is subjected to heating process or upon burning. Is it clear? Now, P block elements, they are further classified into boron family elements, group number 13, carbon family elements, group number 14, and nitrogen family elements, group number 15, oxygen family elements, group number 16, halogen family elements, group number 17, and zero group elements, group number 18. Is it clear? Therefore, by using all these, we have ns2 np to the power of 1 to 6. That is the general electronic configuration of the P block elements, where n is greater than or equal to 2. Okay. Now, they exhibit metallic property, non-metallic property, as well as metalloid property, property. Now, in between these two, in group number 3 to group number 12, that is starting from that of the scandium and ends up to the zinc. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Therefore, group number 4, group number 5, group number 6, group number 7, group number 8, group number 9, group number 10, group number 11. Group number 4, that is titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. These 10 different elements are there. They constitute the D block elements. They are intermediate in between the S block and P block elements. When you write the electronic configuration of these elements, outer electronic configuration of this element, that is given by means of 3D1 4s2 configuration for scandium and 3D2 4s2 configuration and 3D3 4s2 configuration, 3D4 4s2 configuration, but finally it reorganized in the form of 3D5 4s1 configuration. Next, 3D5 4s2 configuration, 3D6 4s2 configuration. So this is this, and 3D7 4s2 configuration, and 3D8 4s2 configuration, 3D9 4s2 configuration. Finally, we have this is 3D10 4s1 configuration and 3D10 4s2 configuration. 3D10 4s2 configuration. This is for scandium electronic configuration. This is for titanium electronic configuration. This is for vanadium electronic configuration. This is for chromium electronic configuration. This is for manganese electronic configuration. This is for cobalt electronic configuration. This is for nickel electronic configuration. This is for copper electronic configuration. This is for last for zinc electronic configuration. This is for copper electronic configuration. Sorry, this is for iron electronic iron. This is for cobalt electronic configuration. This is for nickel electronic configuration. What I am using, this is outer electronic configuration only, because inner atomic orbitals are completely filled. These electrons are not involving in any chemical reactions. Now see, in some cases outer s atomic orbitals are involved in the chemical reaction. Then oxidation state exhibited by means of the scandium, that is equal to +2. For example, scandium shows the lower oxidation state, that is a +2. That is called orbital valency. In some chemical reactions, outer s atomic orbital electrons and inner d atomic orbital electrons are also involved in the chemical reaction. Therefore, we have oxidation number or oxidation state, that would be +3. Now in case of the titanium, outer s atomic orbitals are involved in the chemical reaction, that is orbital valency. In some cases, inner 3d atomic orbital electrons 2 numbers, outer s atomic orbital total 4 numbers of the electrons are involved in the chemical reaction. Therefore, oxidation state exhibited by means of this scandium, oxidation state exhibited by means of titanium is +2 and +4, +2 and +4. Therefore, up to this section, +2, +3 and +4. There is a titanium 4+, that is more stable lower oxidation state is unstable, higher oxidation state is more stable. Therefore, extreme oxidation numbers or oxidation states are there. Lower oxidation state, only 2 electrons are involved. It has ability to attack few more electrons. In higher oxidation state, inner and outer 4 numbers of the electrons are used up, and hence we have +4 oxidation state or +4 oxidation. Now we have vanadium. Now in entrance exam they may ask the oxidation number problems. Therefore, scandium 2 plus or scandium 3 plus. Now this is titanium 2 plus and titanium 4 plus. Titanium 4 plus. Similarly, we have vanadium, 2 oxidation state is minimum and 5 oxidation state is maximum. That is +3 oxidation state and +2 oxidation state and +5 oxidation state in the range. Therefore, +2, +3, +4 and +5. These numbers are involved. Now, in chromium, some cases +1, that is by the utilization of the outer s atomic orbital electrons. By utilizing the d atomic orbital electrons continuously, that is +2, +3, +4, +5 and +6, that is the maximum oxidation state that is exhibited by means of this chromium. See, in your laboratory we have potassium dichromate. What is the color that possesses this potassium dichromate? Orange color. Potassium dichromate is orange color. It is because of chromium oxidation state is +6. Chromium oxidation state is +6. Now see the manganese. Where is the lower oxidation number? That is only the outer s atomic orbital electrons are involved. That is a +2. Similarly, by the utilization of the inner d atomic orbital electrons, +3, +4, +5, +6 and +7. The highest oxidation state that is exhibited by means of manganese, that is +7. See in your laboratory, we have potassium permanganate solution. Potassium permanganate, it is a pink colored solution available in your laboratory. Therefore, potassium permanganate is pink because of manganese oxidation state is +7. Is it clear? Similarly, iron, we have +2 oxidation state and +3 oxidation state because D5 is more stable. D5 is more stable. Therefore, ferrous state and ferric states are possible. Now, what is S and Ec? Stannous, stannic, manganese, manganic, chromous, chromic, and ferrous and ferric. In the pronunciation itself, if suppose we have IC as suffix, that is good oxidizing agent. Ferric is good oxidizing agent. Cupric is a good oxidizing agent. Chromic is a good oxidizing agent. Therefore, any one of the species, if suppose they ends with IC, that is good oxidizing agent. Whereas for lower oxidation numbers, like that of the OUS suffix, ferrous, cuprous, manganese, stannous, like this pronunciation is there. I will be shortcut method, very important. Any chemical compounds, if they ends with the suffix as OUS, then those compounds are good reducing agents because they have ability to give up further electrons. Any one of the species or chemical compound, in pronunciation itself it is found to be IC, like ferric, chromic, cupric, then those are good oxidizing agents. These are good oxidizing agents. Therefore, lowest oxidation state that exhibited by means of this iron is +2 and higher oxidation state that exhibited by means of this iron that is equal to +3. +2 state is called as a ferrous state. See the more salt. If you heard, observe the visibility of the color, that is a pale green color. That is because of the oxidation state of the iron is +2. You are very familiar with ferric. Whenever a piece of iron is exposed to moist air, dry atmosphere has no action. In the presence of humidity or in the presence of moisture, they undergoes oxidation or rusting. The rust is a chemical compound composed of hydrated ferric oxide. See, more salt, rust, both are the compounds of iron. But rust is reddish brown in color with respect to iron I am talking. Rust are the different colors, means metallic oxides having the different colors. Now this ferrous color is a green color, light green, pale green color, and the ferric state is reddish brown in color, reddish brown. Fe3 plus state is unable to give off further more number of the electrons, but Fe2 plus state has ability to give off further electrons, that is one number of the electron. Now in case of zinc, see S atomic orbital is also octet and D atomic orbital is also octet. Therefore in +2 oxidation state, only outer S atomic orbital electrons are used up. Outer atomic orbital electrons, when they are used up, then zinc is found to be Zn2 plus, Zn2 plus, whereas D electrons are not involved. See, starting from the scandium up to copper, successive one number of the electron is involved, that is +2, +3, +2, +3, +4, +2, +3, +4, +5, +1, +2, +3, +4, +5, +6, +1, +2, 2, +6. Manganese, lower oxidation state is +2 because of this S atomic orbital electron. There is a higher oxidation state that is obtained by the successive removal of the D atomic orbital electrons. Therefore, the higher oxidation state is obtained by the utilization of the outer S atomic orbital electrons and inner D atomic orbital electrons. When both these number of the electrons are involved, then it gives the higher oxidation number or higher oxidation state. Now zinc, that is colorless compounds. Zinc compounds are colorless. Zinc compounds are colorless. Why? See, all these elements, they are considered as transition elements. D block elements are transition elements. From left to right, there is scandium to zinc. The oxidation that varies, that is represented by means of this inner atomic orbital electrons are involved, or only outer atomic orbitals are participating in the chemical reactions. And the basis of this we can classify. Now these are called as transition metals. Why? Because S block elements are more electropositive in nature. They have ability to give off the electrons, either one or two numbers. That is why they are susceptible for oxidation reaction. What about the P block elements? See the halogen family elements. Outer we have only 7 number of the electrons. Therefore, it has ability to attract one more number of the electron in order to acquire the nearest noble gas configuration. Therefore, halogen family elements, they have ability to attack one more electron. And previously we have halogen oxygen family elements, they have ability to attack two numbers of the electrons. See, when you add one number of the electron, P5 becomes P6. When you add two numbers of the electron, then it becomes P6. When you add three numbers of the electron, it becomes P6. When you add four numbers of the electron, then it becomes P6. But here, the addition of one electron is very easy. That is why they are considered as electronegative elements. Electronegative elements. Electronegative elements. By the addition of the two numbers of the electron, then it becomes P6 configuration. Therefore, that is electronegativity nature that gradually decreases. If one electron is there, we can add one electron very quickly. That is requirement of the electron is one, we can add quickly. In such cases, they have the initial electronic configuration that should be P5 configuration. Therefore, P5 to P6 is very easy, but P4 to P6 is a little bit tough. P3 to P6 is a little bit tough. Therefore, on the basis of the electronegativity, we can explain. Whereas the S block elements are more electropositive, P block elements are more electronegative. In particular, the halogen family elements are the possess the highest value of the electronegativity. Highest value of the electronegativity. That is why very important question. Afterwards, again discuss fluorine. That is one of the element that belongs to P block in 17th group. That possesses the highest value of the electronegativity. 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 In your entrance exam, they ask the questions, and board exam, they ask one more questions. Name an element shows highest value of the electronegativity. Name an element that shows the highest value of the electronegativity. Fluorine is your answer. And name an element which possesses the highest value of the electropositivity. Highest value of the electropositivity. That is cesium. Down the group, the electropositive nature further increases. Electropositive nature further increases. That is why cesium possesses the highest value of the electropositivity. Very important. Cesium, higher cesium, highest value of electropositivity. Highest value of electropositivity. Highest value of the electropositivity. Therefore, electropositivity of the elements of D block that falls in the range of S block and P block. That is why they are not superior electropositivity like that of the S block elements, not superior electronegativity as that of the P block elements. That is why they are considered as a transition element. Sankranti Dhatugulu, transition elements. Because transition in the properties are there. Sudden shift in the properties are there. That is why from group number 2 to group number 3, sudden jump in the, decrease in the electropositive values. Whereas group number 12 to group number 13, sudden rise in the electronegativity values. Therefore, they are called as a transition elements. Now, very important. Now, all D block elements, like that of starting from scandium to there are 3D atomic orbital is participating in the chemical reaction. 3D atomic orbitals are participating in the chemical reactions. In all the cases, the inner D atomic orbital is adding one number of the electron. Therefore, their electronic configuration seems to be 3D to the power of 1 to 10 and 4s to the power of 1 to 2. 3D to the power of. Therefore, in atomic state, in ionic state also, the D atomic orbital electrons that exhibit certain valency. Therefore, in atomic state, consider this is n, this is n minus 1. Therefore, n minus 1 d to the power of 1 to 10 and ns to the power of 1 to 2. By putting n is equal to 3, by putting n is equal to 3, sorry, n is equal to 4. By putting n is equal to 4, we have this series. Therefore, they are further classified into 3D series elements, 4D series elements and 5D series elements. 3D series, 4D series and 5D series elements. Okay, this is about the general electronic configuration of this D block elements. Now, they form colored compounds. Most of the D block metallic compounds are colored except zinc and cadmium and mercury, because they falls in the the 12th group of the modern period table. Zinc, cadmium and mercury. Because zinc 3d10 4s2 configuration and cadmium 4d10 5s2 configuration and mercury 5d10 6s2 configuration. 5d10 6s2 configuration. Okay. Now these elements, they falls in the D block but not transition elements. Not transition. Zinc, cadmium and mercury. In a entrance exam they ask the question, which one of the following element belongs to D block but not transition? In transition means D atomic orbital electrons, they should involve. But due to the D10 configuration, the D atomic orbital electrons are not participating in the chemical reaction. In all the cases except zinc, cadmium and mercury, the inner D atomic orbital electrons are participating in the chemical reaction. Now, bottom of the modern periodic table. Bottom of the modern periodic table, it consists of 14 cross 2. Bottom of the modern periodic table, 14 cross 2, totally 28 elements are there. Now these 14 different elements, they are called as actinide series elements and lanthanide series elements. They are considered as post-actinides and post-lanthanides. Post-actinide series elements and post-lanthanide series elements. Here, if the outer one is, that is a 4F and 5D and 6s. Usually the elements that falls in the 6th period and 7th period. Whereas if this is 4F atomic orbital, that is innermost atomic orbital, this is inner atomic orbital, this is outer atomic orbital. This is outer atomic orbital, this is inner atomic orbital, this is innermost atomic orbital. Where does the electrons will enter? Electrons will enter in the innermost F atomic orbital. Innermost F atomic orbital. Therefore, usually 6s numbers of the electrons, the outer atomic orbital electrons. Outer atomic orbital electrons, they are completely octet in nature. Inner D atomic orbital electrons are octet in nature, whereas the F atomic orbital electrons, they are not octet in nature. Electrons of the F atomic orbital are participating in the chemical reaction. Therefore, group of elements for which the valence electrons are present in innermost F atomic orbital of an atom are called F block elements. Actinide series elements and lanthanide series elements are considered as F block elements. Why only 14 group is there? In the last class we discussed, whereas the S atomic orbital has capacity for the accumulation of the 2 electrons, whereas the P atomic orbital, that is the 6 electrons, and D atomic orbital, that is 10 number of the electrons, F atomic orbital 14 number of the electrons. That is why 14 groups are there in the modern periodic table in F block. Therefore, 14 groups into 2 periods, That is first, that is called as a post-actinide series element. Second one is called as a post-lanthanide series elements. Therefore, lanthanides and actinides are collectively called as a F block elements. Often they are considered as a inner transition element. Inner transition elements. Inner transition elements. Inner transition elements. Okay. Now this is about the brief classification of the S block elements, P block elements, D block and F block elements. We will discuss in detail once the regular classes commenced. This is brief up of the periodic table. Just I am giving the summary of the period table. In detail we can discuss whenever the regular classes commenced. Now what are the periodic properties? That is the trend in the periodic properties. See, this representation is called down the group. This is called along the period. Along the period and down the group. See, down the group, see, in case of the hydrogen, in case of the helium, 2 shells are there. In case of sodium, 3 shells are there. In case of potassium, 4 shells are there. That is the principal quantum number is equal to 1, principal quantum number 2 is 2, principal quantum number is 3, principal quantum number is 4, and so on. The last we have 7 number of the shells are possible, like that of the fraction. 1, 2, 3, 4, 5, 6, 7. When you move down the group, the number of electrons in the outer shell or outer atomic orbital is fixed. That is 2, 1 number or 2 numbers of the electrons. But the number of shells increases by 1 unit. Number of shells increases by 1 unit. When the number of shells increases by 1 unit, in the center we have nucleus where positive charge is concentrated. Proton is concentrated. Whole density is concentrated. Mass is concentrated. Whereas the last atomic orbital, valence electron is present, which is negatively 1. See here, the nuclear force of attraction or electrostatic force of attraction between the nuclear charge and the outer atomic orbital electrons, that is very less, negligible. Reason, nucleus is far away from the valence electrons. Of course, the inner atomic orbital electrons are there very close to the nucleus, but they are not participating in the chemical reaction because of their complete octet state of the atomic orbitals. Higher atomic orbital or valence orbital, these electrons are participating in the chemical reaction. Therefore, valence electrons go away from that of the nucleus. Therefore, the size of an atom, that is the distance between the center of the nucleus to the outer atomic orbital, where we can observe the valence electron, that distance that gradually increases down the group. Therefore, atomic size of lithium is greater than hydrogen. Atomic size of sodium is greater than lithium and greater than hydrogen. Atomic size of the potassium is greater than sodium, greater than lithium, greater than hydrogen. Similarly, atomic size of the cesium, that is greater than that of the rubidium, greater than potassium, greater than sodium, greater than lithium, greater than hydrogen. Therefore, as we move down the group, atomic size gradually increases. Along the period, the number of electrons are added to the outer atomic orbital. Therefore, outer atomic orbital electrons that gradually increases, but the number of shells remains constant. Number of shells remains constant and number of the electrons that gradually increases. This increases the nuclear force of attraction or electrostatic force of attraction between the nuclear charge and the outermost atomic orbital electrons. Therefore, outer atomic orbital electrons have more affinity with of the nucleus, they shrink towards that of the nucleus. Therefore, the size that gradually decreases.